In this study, you must know how to perform the Newton finite divided difference interpolating polynomials to find the interpolation result. In this graph, two measurement points are given here, where the y-axis is the function x versus the x-axis here. This black line is the actual solution, however, is unknown in many cases. We will use it as the benchmark to check the accuracy of the interpolation result. By using these 2 points, we can connect them in a straight line. From this linear line, then we can find the interpolation result, for example, f1x. The number 1 here indicates the first order Newton method, which is the linear interpolation method. Basically, if the point at x0 and x1 are given here, then you want to find out what is the interpolate data at point x here. We can use this formula, which is the Newton linear interpolation method, to find the f1x here. For example, if the measure points are given 3, 4 and 8, 9 here, let's substitute inside this formula, then you should get this. And you can use this formula to predict the interpolate data within this region from x0 to x1. For example, let's say you want to predict the x value equal to 3 here. You can substitute 3 inside. So you calculate 3 minus 3 equal to 0, multiply here also 0. 0 plus 4, you obtain f1x to be 4. Therefore, when your x equal to 3, f1x equal to 4. So you see that the interpolate result is the same with the measurement result here. By using the same method, you can interpolate the data within this region. So let's say the x is equal to 5. Substitute the 5 inside here, then compute, you should obtain the answer equal to 6. So you obtain the f1x equal to 6 when your x equal to 5 here. In the graph, you have over here equal to 6. By using this Newton linear interpolation formula, we can make interpolation between two measured data. Next, we will discuss the derivation to obtain this formula. First of all, let's compute the slope between these 2 points. You need to take the delta f divided by delta x. So your delta f is equal to fx1 minus fx0, and your delta x is equal to x1 minus x0. So this is your first slope. Assume that you want to interpolate data at x, f1x here. So we can also find the slope by taking delta f divided by delta x. In this case, delta f is f1x minus with fx0, and your delta x is x minus x0. Then you obtain the second slope. First slope is the same with the second slope. Then you should obtain this equation. To obtain the f1x on your left hand side, let's multiply with the x minus x0. Then this term will be cancelled. It will appear here, x minus x0. You continue to add fx0 on both sides. Then this term will be cancelled, and on your right hand side, you have this plus this term. With that, we success to obtain the first order Newton interpolation method, which is the linear interpolation. So this term is the finite divided difference approximation to the first derivative. And in symbol, you should have this. The accuracy of this method is highly dependent on the step size here. So as long as this delta x is small, then the accuracy of the first derivative here will be better. If you benchmark with the actual data, with the interpolated data that you obtain from the linear interpolation, if you see the error is large between the actual data and the interpolation result, then you should reduce the step size in order to improve the accuracy. Or you can improve the order from first order to second order, which is the quadratic interpolation, in order to reduce the error. Before we continue, bear in your mind, if you see a notation like this, where you have the f in the bracket of x0, x1, this notation is equal to the first derivative formula here, where you have the function in terms of x0 and x1. If you change the x number to x2 and x3, then you should expect here you have x3, x minus x2, like this. Before we continue, bear in your mind we can use this notation to represent the first derivative approximation here. So f in the bracket x1, x0 is equal to this formula. If you change the number to 4 and 3, then this formula has the function in terms of x4 and x3, like this. In this case, we have the second order Newton interpolation method, which is the quadratic interpolation. This is the quadratic interpolation formula. To use this formula, we need at least 3 measure points, such as these 3 points. Then we can find the interpolate data in the blue color here, which can be written as x f2x. For example, if the measure data is given in this table and you are going to find out what is the x fx when your x is equal to 3 here. First of all, we assume this to be 0.0, 0.1, 0.2. Then you can substitute the x0, x1, x2 as well as the corresponding fx into this formula. Then substitute the x equal to 3 inside the formula as well. You should be able to obtain the f2x, which is equal to 7.25. 2 here indicate that we are using the second order method in order to interpolate the solution. If we compare the quadratic interpolation solution, which is in blue, with the actual solution in black, the error between the actual and the interpolated result is smaller. Therefore, the second order interpolation method has a better accuracy compared to the first order. Previously, we can simplify this term by using the f in the bracket of x1 and x0. It means the first derivative approximation, and the bracket here means the finite divided difference. If we look at the second term here, so this term is the first derivative of f. This is also first derivative of f, x1 and x0. The whole term here is the second derivative approximation, where we can further simplify it to be f in the bracket of x2, x1 and x0. We take x2, which is the first element, minus with the x0 in the denominator here. Then we take x2 and x1 for the first derivative here, minus with the f x1, x0 in the first derivative here. So there is a missing f here, so please correct this. We can also apply the third order Newton interpolation method, which is the cubic interpolation. So this is the formula. In the first order, you have these two terms, where you have the first derivative approximation f x1, x0. In the second order interpolation, you have additional one term here, where you have the second derivative approximation and you multiply it with an extra x minus x1. In the third order interpolation method, now you have additional term for the third derivative approximation that requires 4 points. And you need to multiply with additional term x minus x2. In numerical analysis, this bracket means that it is the finite divided difference function. For the first derivative approximation, you need 2 points to compute the derivative. You need 3 points for the second derivative approximation and 4 points for the third derivative approximation. At the denominator here, we always take the first element to be the first number here. So for the second and third derivative, we also take the first element here. For the element here, you need to take the last element here. By repeating the same procedure, you take the last element for the element here. If you have two numbers, then you take the fx1 minus fx0. If you have three numbers, we take the first two numbers to be the first derivative here, and then the next two numbers to be the first derivative here. They are missing f here, so please correct it. By using the same approach, if you have 4 numbers, then you take 3 numbers for the second derivative, and then the next 3 numbers for the next second derivative. You should know how to read and perform the notation for the finite divided difference function here. This is the general formula for the Newton interpolation method, where you can see you can use this formula to form n order interpolation method. For the first order, n is equal to 1 and you need 2 points, which is x0 and x1. Since you don't have x2, then x2 and above you can cancel, so your f1 formula is equal to this. And you need to read the bracket term here. So this bracket function evaluations are the finite divided difference. Since you have 2 points, then we put the smaller number x0 at the last element and x1 at the first element. So if you look at this equation, it's the same with the equation that we applied earlier. If you want to apply the third interpolation method, then n equal to 3, you need 4 points. Let's have the x0 until x3. Since n equal to 3, then you can substitute inside this formula 3 minus 1, you obtain 2 here. 3, and this one is 2, so you continue x1 until 0. So initially you have f for the x0, first point, then you continue with the f x1 and x0. Next you continue with the f x2 to x0. Then lastly you have the f x3 to x0. So for the derivative approximation, you multiply it with the x minus x0, which is the first point. Then you multiply it with the x0 as well as additional x minus x1. You multiply it with the x minus x0, which is this point. For this derivative, you multiply it with the x0 here, x1 here, and you stop. For the last derivative here, you multiply with the x minus x0 here, x minus x1 here, and lastly you have the x2. To find the finite difference for this term, we can use this equation. Since your n is equal to 3, you can substitute. So 3 minus 1, you have 2, then x1 and x0. So n here is 3, 2, so x1, then you stop. So here you have 3 minus 1, you have 2, this one is 1, x0, and you stop. So this one we replace by 3. So this is the third derivative approximation for this term. If you compare this equation, then you will see this is exactly the same with the previous equation that we applied. So you can use this equation to find the n order interpolation formula that you want. In this case, we have a function fx equal to ln x. Let us assume that this function is unknown in actual. 2 measure points are provided here at x equal to 1 and x equal to 6. This is the information for the point 0, and this is the information for the point 1. We always arrange the x0 and x1 such a way that x0 must be smaller than x1. In this example, we want to predict what is the value at x equal to 2 here. So at x equal to 2, what will be the value? We can solve this by using this linear interpolation formula, which is a first order method. By substituting all the parameters inside, you can obtain the function at point 2 to be this answer. So this is your interpolate result. When you compare it with the actual answer here, which is ln 2, so ln 2 is equal to 0.69 something here. The true percent relative error is equal to the true answer minus with the interpolate result divided by the true answer. So this is the error. To reduce the error, instead of using these 2 points to interpolate the result at x equal to 2 here, in this case, we are using a smaller interval. We do not consider this point, and in this case, we choose a smaller interval. By using the same method, which is the linear interpolation, we can predict the function at point 2 here, and this is the answer, 0.46. When we compare this interpolate result with the true answer here, which is ln 2, we obtain the true percent relative error to be 33%. So it means that by reducing the interval, the accuracy of the solution can be improved. Where you can see the interpolate result is closer to the true answer here, which indicates the reduction of error. Let us interpolate the result for x equal to 2 by using these 3 points. In this case, we can use the second order method, which is the quadratic interpolation. In this formula, you have the f bracket x1, x0, which is the first derivative approximation that can be computed by using this formula. And you have the f in the bracket of x2, x1, x0. So this is the second derivative approximation that can be computed by using this formula. So after you substitute all the parameters inside this formula, you should obtain the function at point 2 to be 0.565. The true percent relative error is 18.4%. In this example, we show you that we can further reduce the error by choosing a higher order. So the second order interpolation method has a better accuracy compared to the first order. In the engineering application, we can use the interpolation for trend analysis. For example, we measure the velocity at various times here, and we would like to know at t equal to 10, which is over here, what will be the velocity. And we can obtain this result by using interpolation. In this case, we apply the Newton interpolation method to solve the problem. So we apply the first order until fourth order, and in the first order, we need 2 measure points. So we choose these 2 points to interpolate the velocity at t equal to 10 here. So from this result, we obtain the velocity here. Then we continue with the second order interpolation method that requires 3 measure points. So by using these 3 measure points, you can interpolate the velocity at t equal to 10 here to be this answer. Next, we proceed with the third order interpolation method, which requires 4 measure points. Then you predict the interpolate result to be this. And lastly, you continue with the fourth order interpolation method, and this is the interpolate result by using these 5 measure points. We cannot apply higher order interpolation methods such as 5, 6 and so on because we only have 5 measure points. So you should know that for n order interpolation method, you must have n plus 1 point. So you can see the black line here is the interpolation result by using first order until fourth order interpolation method. In actual scenario, we only have 5 measurement points, and the actual velocity at other points is unknown. Therefore, we cannot check and compute the true percent relative error, so we cannot tell which order has the best interpolation result based on this. In this case, we need to take the physical consideration of the falling parasitic case to evaluate the appropriateness of this result. From Newton's law, mg minus the drag force is equal to ma, and a is equal to first derivative of velocity. When the mg is larger than the drag force, in this case, the mass will experience the change in terms of velocity, and the velocity will increase over the time. So this is the transient process where the velocity is changing. In many cases, the drag force is related to the velocity. If the velocity increases, the drag force will be increased as well. So if the drag force increase up to a level same with the mg minus drag force will be equal to 0, which means the mass will not experience change in terms of velocity, and your velocity will be maintained the same, and we will have the steady state condition. So this is the physical process of a falling parachute, and during the fall, the velocity never reduces. Based on the understanding of the physical system, let us check the interpolation result here. So for the first case, order result seems not logic here. The velocity at t equal to 10 is larger than the velocity at t equal to 13 here. Third order method also have the same issue where the velocity at this point is larger than t equal to 13. These two results are not appropriate because it do not agree with the physical process where the velocity should not decrease over the time. On the other hand, the first and second order interpolation are more appropriate. As you can see, it increased over the time within these two regions. Second order method gives the most accurate result since it can extrapolate the other region as well. Compared to the first order method, in this example, it shows that it's not a straightforward task to obtain the best order of the interpolation method. High order interpolation methods such as the fourth and third order method here may not have the best accuracy compared to low order methods such as the second and first order in this example. In actual scenario, we need to consider the physical consideration to choose the best order for the interpolation. Besides that, we can also predict the truncation error for the first order Newton interpolation method by using the remainder here. R1 is the remainder for the first order, R2 is the remainder for the second order, R3 is for third, R4 is for fourth order Newton interpolation method. If you find the remainder at the second order here to be lowest at x equal to 10 here, compared to the other remainder here that you compute, then we say this order gives the best accuracy and we will choose this for further analysis. For example, previously you applied the first order Newton interpolation method, which is the linear interpolation, to solve this problem. In many cases, the true value is unknown. Therefore, you cannot compute the true percent relative error. You can predict the error by using the remainder for the first order, which is given by this equation. Since you want to interpolate at x equal to 2, then you find the remainder at 2, which is this answer. In this example, we are using the first order linear interpolation method to solve the problem, but with smaller intervals. Since it is a first order interpolation method, therefore your remainder is R1 as well, which can be given by this formula. Substitute x equal to 2, you obtain the remainder to be this answer. And if you compare to the previous example, this error is smaller. Therefore, by having a smaller interval, we can obtain a better accuracy. Now we are applying the second order quadratic interpolation to solve this problem. And we can predict the error by using the remainder R2. Then you can compute the remainder at x equal to 2 to be this answer. When you compare to the previous case, this answer is the lowest remainder. So we can say that the second order quadratic interpolation has a better accuracy compared to the linear interpolation, which is using the first order interpolation method to solve the problem. You should learn how to use the remainder to estimate the interpolation error by using various order. In most of the case, the true value is not provided. Therefore, you cannot determine the true percent relative error. However, by using the remainder method, you can still predict the error and use it to choose the best order for interpolation.